Let's explore the basic operation of the MOSFET through the simulation in the Cadence Virtuoso. To explore, I'm taking a simple circuit of MOS transistor which is connected with DC voltage sources where at a gate terminal and a drain terminal through RD. So now I will be taking 5 operating points for the different values of RD. When the small value of RD considered from the 0 ohms, 100 ohms, 200, 300, and finally I give it the value of RD as 1.5 kilo ohms. If I keep a huge value of the resistance RD equal to 1.5 kilo ohms, there will be limit in the current. So with the limit of the current, what might be the changes that occurred in the region of operation of the MOS transistor and how it will be get affected, how the current will be changed. That is all the things that we discuss now. And now, as I'm saying that operating points, let me explain it over here where a MOS transistor is connected with the VGS, this is VGS, right? This is VGS. I'm keeping a fixed voltage over here, gate voltage is 1, so I'm considering the VGS equal to 1. And I'm going with the different operating points where initially RD I'm keeping as 0 ohms. 0 ohms. So I consider that there will be a VDD of 1.8 volts. There will be sufficient current will be conducted because that limiting resistor is very small. So which will not limit the current, will be conducting the huge current. So the transistor, how exactly he is expecting that huge current will be supplied. There will be sufficient biasing was provided so that the transistor will be operating in the saturation region. Even I have verified through the special notation called region where it is in the second region, right? And also I have to verify whether the transistor goes into the linear region. When it is showing the indication of region 1, it means it is in the linear region. So now there are two cases where in the second case I'm going with the linear region, in the first case I'm going with the saturation region. So now I'll explore, right, how the transistor is operated in the saturation region, what will be the thing happens, and when it goes to the linear region what will be the thing happens, we separately discuss one by one. And before that, let me show you how the notations got shown over here on the schematic in the Cadence Virtuoso. So here this is the Cadence Virtuoso. Let me go with the ADL or Master also. So I will be taking my analysis DC and I will be selecting the operating point and let me run once and let me come on to the schematic, and where I can show you whatever the VDS, it's around 1.8 volts that I give. So this is where 1.8 volts will be supplied. The same 1.8 volts will be connected over here and supplied over here. As that RD in the first case I'm keeping it equal to 0 ohms. I will be keeping RD is 0 ohms. Right. So here RD, let me keep it at 0. Let me keep it 0 and let me simulate it once again. Yes. After the simulation process is completed, then you have to go with the annotations. You have to give right click on the transistor and you have to select the annotations and you have to select the operating point, DC operating points. Then again you have to give the right click and go with the annotations and go with the setup. And in the setup, what kind of annotations you are expecting, that you have to list out and you have to enable all the annotations. So ID is required where I wanted to check whether the current is how much that I wanted to check. So I will be enabling the ID. VGS, as already know that VGS value is 1 volt, we are not changing, that's why VGS is not required. VDS also shown over here, so it's not required. GM value sometimes is required, we'll keep it. And I need threshold voltage where I have to calculate the current which is flowing theoretically across the transistor. So VGS is VTH is required. Let me keep the VTH over here. And instead of these two, I need the parameter called beta effective. So let me take the beta effective, and I just need the R on also. right? So these are the three parameters required to calculate the current. So where do we use the parameters? We'll discuss one by one and give a play. So automatically these parameters going to be shown over here. So after you get these all parameters, you have to, oh, one more thing, you have to annotate the region of operation also, because we need to know whether the transistor is operated in the same region or not. So GM is not required as of now. So let me remove this one and let me keep a region of operation with the notation region and apply. So it is operated in the second region. It is nothing but a transistor. When it shows the indication that annotation with the 2, it means the transistor is operated in the saturation region. So this is the same thing that I can show it and explain now. For the first operating point, as I have the simulation results like this, the ID current which is conducted of this much, which is operated in the second region, B effective of this one, beta effective of this one, VTH of this one. So for these all values, what I do is I will be calculating theoretically how much the current going to be conducted and how much current is expected by the transistor. That both things we will calculate theoretically and practically, as that practically tool gives the value of that ID is conducted equal to 765 micro. So I can put the same value, the practical value of that ID equal to 765 microamperes. Now let us calculate that theoretically. When the transistor is operated in the saturation region, I know that current equation ID equal to half mu COX W by L times of VGS minus VTH whole square. So I don't have these all parameters, but tool gives that the combination of all these parameters as a BF. So beta value, let me substitute over here of beta effective, let me put it over here, and VGS minus VTH whole square. So we have all the values over here of beta effective is 2.30 milli into 10 to the power of minus 3, and VTH value is 1. VTH value is 1, and VGS value equal to 1. VGS value we are keeping it is 1, and VTH value is 184 milli. So I will be considering is 0.184 whole square. So if I calculate this one, if I calculate that one, so which will be around 765. We have 10 to the power of minus 3, so it will be the value of 765 microamperes. So we can put that value as it is. So what theoretically the current which will be flowing over there when it is in the saturation region is 765 microamperes. I can say that the transistor will be expecting of this much current. The transistor is expecting of this much current. The biasing circuit over here, which will be pumping huge current, whatever that expected current, more than that he is trying to pump, so that the transistor will be operated for the analog application, and it is also operated for the saturation region, operated in the saturation region. So theoretical calculation and practical calculations both will be same. And I will be showing through the analogy where I can show you that analogy where the transistor is biased with the different values of the load current, where initially that load resistance equal to 0 ohms, and load resistance equal to 100 ohms, and load resistance equal to 1.2 kilo ohms, and finally I will be keeping the load resistance of 1.4 kilo ohms. So if I keep the different values of load resistance, and if I consider that each operating point, and if I see the transistor, for the first case it is operated in the saturation, second case also operated in the saturation region, third case also operated in the saturation region, but in the fourth case I can show you it is operated in the linear region. So here it is operated in the linear, here saturation, so here also saturation, and here also saturation, right? So what might be the issue happen? So why the transistor is going into the linear region? The reason for the transistor go into the linear region is, in all the cases where I'm giving the control voltage at the gate is same, and I'm giving the supply voltage is also same, just I change that RD values. So when I keep that RD value is very high, which limits the current flow, when the current is expected by the transistor will be supplied by the biasing circuit, definitely the transistor will be operating in the saturation region. But in this case, the transistor won't be operating in the saturation region. That might be only one reason, where there is a huge value of the resistance is connected over here, so which limits the current, which will not supply the amount of the current required by the transistor. When the current is not more than that expected, that that case this electrical node supplied with less amount of the current than conducted out, then that electrical node will be that more charge is going away from that node, so that the voltage level at the node will be reduced. So once the voltage level is reduced, so this is what the node which indicates that VDS of the transistor, this node indicates the VGS of the transistor. As the VDS decreases, as we know that condition for the saturation is VGS minus VTH, this is the level, right, where where above this level my VDS should be maintained. So VDS should be more than this one. But what happening, there is no sufficient amount of the current is going into that electrical node, no sufficient charge is going to that electrical node, then the charge is leaving. So this particular electrical node will be the voltage level of the electrical node will be reduced, so that the VDS value will be reduced, so that the condition for the transistor to operate in the saturation region failed. So that's where the transistor will go into the linear region. So now we'll see that same thing through the analogy also, where that analogy shows when there is a sufficient water is available in the water tank, as you open the tap, the control voltage over the tap I consider as a VGS, and the effective voltage is represented as a VGS minus VTH. So when VGS equal to 1 volt and VTH equal to 0.84, let us suppose 0.184. So this much voltage when we apply, we open the tap by some amount. So the corresponding current the transistor has already calculated 765 microamperes. So it will be expecting 765 microamperes, which will be conducted across this one. For the given voltage, when you open the tap by some amount, the corresponding current will be expected to conduct of this much. So for this, what we need to make sure is, in the first case and second case, third case and fourth case, what happening is, in the first case I can see the drain is, this is in the water tank, where the water tank will be supplied with the biasing of 1.8, and the RD is connected over here. So some amount of the water will fall into the electrical node and fall into the water tank, and the water will be coming to flow across the MOSFET. So as we see in the first case, there will be huge amount of the current will be coming over here. So that water tank will be very much high. Water level across the water tank is very high. So which I can indicate it is 1.8. So in the second case, what happening? Because we are keeping the resistance value is very high, so that water flow with respect to the previous case is reduced. So water level across the tank also reduced. So this is 1.7. So now we have to make sure, as you increase that RD, the water tank level will be reduced as it is, obviously, right? We have to make sure that it will be reduced to what extent it is possible, it can be allowed. So as we know that the condition is VDS, this is the water level we can represent as a VDS. So VDS should be greater than VGS minus VTH. As VGS minus VTH is this much, 1 minus 0.184, this value is nothing but around 8 16 millivolts. So this will be the level. 816 millivolts. So this is nothing but VGS minus VTH. So my water level across the water tank should be more than this one. If it is more than this one, the transistor will be in the saturation. If come below, it will be going into the linear region. So now what might be the condition is, as you are increasing that RT, so that the water level is reduced. So if the water level is reduced up to 816, right, up to 816. So this is the fourth case. Only in the fourth case it failed to maintain the voltage across the water tank is 816. So here also maintaining 816, here also maintaining 816, here also maintaining 816. So we have to make sure that in the water tank there should be sufficient water, then only the control mechanism will take place. So we have to maintain the water level across the water tank should be more than this. So then only the water flow which will be controlled by the gate. So this is the first case where I'm trying to change that RT different values and trying to do the sweep now, and I will be showing the simulation in that. As of now, we just verified the operating point. Now I'll see the DC sweep, the component parameter. From I do the sweep for the different cases of RT. I'm keeping that RT equal to 100 ohms, 200 ohms, 300 ohms, and 400 ohms. So as we know that for the multiple values of RT, where I can show you, if RT value is changed, the current which is going to be supplied is also changed. So he is going to give that fuse current less than that current, or whatever the changes across the drain terminal, the changes across the drain terminal current will not be affected, because if even huge amount of the current will be conducted, the transistor will not consider that huge current to flow. As per the gate required VGS minus VTH, as per that as we have calculated 732 micro, it only conducts the 732 micro everywhere, even though the voltage or current which you are biasing at the drain terminal, whatever the value it is, so the current flow will be the same. This is the basic operation of the MOSFET to be remembered, right? We have to make sure this basic concept should be clear for the MOSFET. The MOSFET, when it is in the operation, when it is operated in the saturation region, the drain terminal, whatever the current it pumps, right, whatever the current which gives, so the drain current over there, MOS transistor takes the same amount of the current in all the cases. So it will be the calculated current what we have done it previously, that much itself it will be taken. So now we'll see that the same thing here also. As we see the transistor is operating in the saturation region, I can copy the same thing here and I can show you. Yes, so I got the waveforms like this. So here the waveform showing that there will be two regions. This is a linear region, this is the saturation region. So how can I differentiate the linear region and saturation region? As the VDS I'm changing it on the x-axis, I'm trying to observe the change of the ID. So where I can split this one, this is the level where VDS is very high and VDS is very low. So as we know that once you sufficiently provide the VDS, water tank water level should be high. When water level is high, definitely the transistor will be operating in the saturation region. So in the same way, when there is a sufficient water is available, VDS is very very high, so then transistor will be operating in the saturation. So I can say that this is the only reason the transistor is operating in the saturation region. And I can observe that when it is operating in the saturation region from the waveforms, if the RD value is differ 100 ohms, 200 ohms, 300 ohms, whatever the RD you keep it, in all the cases, if I change the RD, the current flow also should be changed. But what happening, the current flow is at a same level, it is around 765 microamperes. As per the transistor is expecting the current, so whatever the resistance you keep it, it will be conducting the same amount of the current, 765 microamperes. So this is the very important operation where current conduction point of view, the transistor is controlling element. As per the gate voltage control, the controlled current should be conducted in the saturation region. This is proved as per the practical value of the current and the theoretical value of the current at one operating point, at a multiple values of VDS also observed, right? So now then we go into next case when the transistor is operated in the linear region. So now next case where the transistor when it will be operated in the linear region. So when the resistance is very huge, when the resistance is very high, which limits the very high current. So when it limits more, so water which comes here and the going water is this much comes here, it is very limited, so that water level will be reduced. Once the water level is reduced, once the water tank is empty, so this is open for flowing this much current because the water tank is empty, so the controlling current will not be conducted. So the problem that we face, the transistor will go into the linear region, that when the current is not sufficiently conducted, biasing circuit is not sufficiently designed to conduct that more current. So that's what practically we check. So here we are expecting the transistor to conduct of this much to operate in the saturation region. So instead of that, when RD is connected of 1.5 kilo ohms, so there is a huge value of the resistance is connected. So the transistor went into the linear region. That's what I can observe over here with the notation. So when it is going into the linear region, so here I can observe that the transistor is expecting of this much current as per the voltage gate control. When you open the tap of this much, so you will be expecting of this much current. So here also you will be expecting the same current. So if I consider the water tank over here, so the current which is expected over here, downwards will be around 765. And but the current which will be supplied by this biasing circuit due to the limit, so 727 itself will be conducted. So now if you see that continuously it is conducting very less amount than the current which is flowing, so the charge which is coming into the electrical more than that charge is going away, so that continuously the water level will be reduced, so VDS value of the transistor is reduced. Once the water tank is empty, not sufficiently have the water across the water tank, if you open the tap also there is sufficient current will not be conducted as per the control. So it means the transistor is going away from the saturation. Now we can see that same with the notation of region. It is now in the linear region. So now let us go with the calculation of the transistor current in the linear region, theoretical and practically. So now if you go with the calculation, the practical calculation, we can see that the practically how much that ID was conducted, which shown in the tool is 727 micro, 727 microamperes. So now we calculate that theoretically also. So we calculate that theoretically also. So if I calculate that theoretically, as we know that current equation for the transistor in the linear region of operation is mu COX W by L times of VGS minus VTH, VGS minus VTH into VDS minus VDS whole square by 2. This will be the current equation. So as we have the current equation, this one is considered as a beta effective, which is given around 2.18 into 10 to the power of minus 3 into VGS value. VGS is nothing but the same VGS I am trying to maintain in all the cases. VGS equal to 1 volt and VTH equal to 0.184 into VDS. So you can see that the drain voltage with respect to source is anyhow grounded. So drain voltage is nothing but VDS now. We can see that 0.708 minus 0.708 whole square by 2. So this will be the quantity, the current only conducted across the transistor. So if I do the calculation, so 0. So this will be the value around 713, 713, 713 microamperes. If I do that exact calculations point to point, if I do it 562 something, if I put it, so what exactly the current which is flowing, that theoretical and practical I can match. So this is the practical value and this is the theoretical value I can match. And this is the first method where I have done the calculation, that I can do the calculation with the second method also. So let me show the second method, where my equivalent circuit for the given circuit is, where there is a RD is connected, where RD is connected of as we keep 1.5 kilo ohms, and below that we have a transistor. As we know, the transistor is operated in the linear region, so it will be like a on switch. So where we have analog application linearity, we have here, we don't have the linearity with respect to input change. So just it is a on switch, on and off switch. For the digital applications we can make use the transistor when it is operated in the saturation linear region. So it will be R on, it offers that R on when it is a on switch. So that I am going to replace with the some resistance with the value of R on, and then finally it is connected to the ground. So their supply voltage VDD is given around 1.8 volts. So this is the simple circuit. Now how exactly the current flows? Here also should conduct the same current. So now I can calculate that ID equal to R on, which I already calculated. R on, which we have calculated here. R on is not shown. So R on we have to calculate here. So that we have got it in the tool. Let us get the value from the tool. Let me keep that RD equal to 1.5 kilo ohms. 1.5 kilo ohms, and let me run. I don't need the waveform, just I need the sweep. I need the operating point. So let me keep the operating point itself. Let me select the operating point itself, and let me run. So here we got that R on equal to 973.7. 973.7, sorry, 0.7 ohms. So now this Rn value equal to 973.7 ohms. So as we know that resistance of this much and this much in series, so there will be a total current is nothing but ID is nothing but VDD by supply voltage by 1.8 volts by the total resistance 1.5 kilo ohms plus 973.7 ohms. So if I calculate that, I get around 1.8 divided by plus 973. So we got it around 0.7 milli. It's around 727 micro. So approximately we get it around 724 microamperes. So 727 microamperes that we got it theoretically, sorry, practically. So this is what we got it theoretically. So through the value which you know are on, so this is the way you calculate the total current, and if you know these parameters, this is the way to calculate. So theoretically we can calculate the total current which is flowing across the transistor MOSFET can be calculated with these two methods. Simulation. Let us do the simulation on the power state also. Let me do the connection, circuit connection. So here I have the water tank where amount of the water comes into the electrical node into the water tank should be more than the current which is going to be conducted or expected by the MOS transistor. So let me connect that. So this is the wire through which this electrical node where it will be pumped with a huge amount of the current and will be discharged through the transistor when it is open, right? When you open the tap and when you close the tap, that is done by the VGS voltage that we are applying. As per the circuit diagram, that we have 1 volt connected across the VGS, and the VDS is supplied of 1.8 volts VDD, and the resistance value initially we keep it around 1.5 kilo ohms. So now if you see that, and one more thing, we have to make sure the threshold voltage and the beta value as per the notations shown in the schematic in the Virtuoso tool. So here the beta value is shown around 2.188 milli, 2.188, 2.188 milli, 2.188 milli, and VTH value is 184.5. 184.5 milli. So as per the two values, as we have already calculated, we just give the beta value and we give the VTH value. It will calculate and it expects the current of this much. So this theoretically we calculate, and practically it was done by the tool, and it will be expecting the current of, show over here. So this much current will be expected. So expected current is 2, as I shown it already, it will be expected the current of 732 micro. But what happening, 732 micro is not going to be supplied because we are keeping a resistance of 1.5, huge resistance which limits the current. So the transistor, we can see it is operated in the linear region. So this is place where you can see that all the annotations for the transistor. So it was operated in the linear region when the VGS equal to 1 volt, VDS equal to 722 millivolts. So we have to make sure this 722 should be more than the, here the voltage should be more than the water voltage. So water voltage is VGS of this much and VTH of this much. So VGS minus VTH of this one, and 1000 milli minus 184 milli, around 816 milli. So 816 millivolts the transistor drain voltage need to maintain. So 816 millivolts is not maintained because this electrical node is becoming empty, because that fuse current is going to be grounded than the current which is going to be supplied. So this electrical node going not well, voltage level across the electrical node is becoming this much. So the transistor will be going into the linear region. That is clear. So now transistor, we can see it is in the linear region. So now what we do, we have to bring the transistor again into the saturation region. So this electrical node need to be boosted with pumping more amount of the current by keeping this resistance value less than that. So 1.3, let me keep it, and let me check. Let me check. So 854, as we are expecting, this water tank should be having enough water so that it will be pumping that required current. So water level, what I'm expecting is, as per the calculation that we have done, the water level should be 816 millivolts. So 816 millivolts, it should be maintained 816 millivolts. If this is the case where the resistance value is reduced so that it is maintained the water level expected value as per the expected value. So 854, if it is maintained, so that the transistor, now we can see it is operated in the saturation region.